In the F10 equation, if we didn't find a solution, integer solution, x, then there can be no data dependence between these two pairs of array references. But if there is an integer solution, then it's not certain that there is a data dependence. We must check that the solutions are within the loop bounds. And to do that, we use a technique published by Fourier, 1827. And it's sometimes called Fourier-Motzkin, and at other times Fourier elimination. It was the idea was by Fourier. Okay, and it works with the real case. So even if it concludes that there is a solution, it's not certain that there is an integer solution. Determining whether there is an integer solution to a system of linear inequalities is NP-complete. But there are cases that we can draw more conclusions from, such as if we get something like this, then there can be no integer solution, obviously. And if we have a sufficiently small range here, we may want to try setting xi to different integers and see if there still is a real solution. So how does it work? We have a system of linear inequalities, and what we do is to eliminate one variable at a time. So we start with x2 in this case. To do that, we sort them, the inequalities, so that we have all positive first and then the negative. Okay, and last the zero, but that doesn't matter now. So we do that, and then we divide by the coefficient and change those with negative to greater than instead. And we will have the system on this format, on this form. What we can see now is that since this should be less than or equal to x2, it must be less than or equal to each of these. And therefore we can remove x2 or eliminate x2. Okay, that is what we do. Oops. So we combine them and get two new inequalities, and we can simplify this and get this. From there we can conclude that there is a real solution. X1 as this, like this, and therefore we would say that, okay, and there is a solution for x2 as well. And we would say that there is a data dependence. Here is the pseudocode for Fourier-Motzkin elimination, and we will not go into this in a particular detail. Okay, but everything is explained in the example. Okay, so let's summarize data dependence analysis. This introduction to it. First, the GCD test. We set up this. These are the two references, and we try to find a solution. We take this A and minus B and say that we have a new matrix A for which we want to find a solution in the T variables. And if we find that, that means there is an integer solution to this, then we use the Fourier-Motzkin test to see if the solution is within the loop bounds. Okay, so say we found that. Then we have X is T times U, the unimodular matrix. And what we need to do then is to take the I and the J parts. The first left part of X is the index variables of one of the references, and the second half is for the other reference. Okay, so we want to express the index variables for each reference as well, using T and the unimodular matrix, which we can do like this. Okay, and what do we do then? Then we insert them into the loop bounds. So the loop bounds are described as this, like this, and we require, obviously, that both references should be within the loop bounds. So we set up this and use Fourier-Motzkin elimination to determine if there is a real solution to this. And if there is a real solution, we conservatively believe that there may be an integer solution as well.